thank you all so much for the opportunity to come chat. As we mentioned, this is the same project, a cloud-native approach to reproducible machine learning. And I know that we've all very much focused on a critical portion of the infrastructure around feature stores, which is absolutely critical to any kind of large-scale deployment. Building an overall pipeline that includes something like a feature store and builds an abstraction layer for models and for engineers looking to go off and build. But just like we were talking about in the experience before, or excuse me, in the talk before, I think the difference between data scientists and ML engineers over time does need to get to as close to zero as possible. Because right now, unfortunately, these data scientists are a bit on an island. No matter how great feature stores and production platforms and things are, they're mostly developing on their local machine and really in an isolated way, which is a bummer because that will slow the move to production. So today I'm going to talk to you a little bit about how we got here, and then talk to you about the start of this new project. I like to put this slide first just to characterize or classify for everyone. I'm going to try and be very consistent, but terms are all very weird. When I say program, I mean the entire thing, an algorithm plus the data structures plus the workflow, not the data, but the data structures. And when I say an experiment, I mean a single run of that. And I'm sure I'm going to get it wrong, but I just like to do my definitions up front. So I've talked about this for a long time. One of the biggest problems with ML is it's very hard to even open a newspaper or article, a journal today, and not see some fantastic use of ML. The one that I like to talk about quite a lot is Google. This is a public blog post that they talked about where they talked about using ML against their data centers. And what they wanted to do is drive product usage efficiency as close to 1 as possible. So the amount of power going in, the amount of efficiency coming out. And they hired some really smart people at data center engineering, and they're very proud of themselves. But when they came along and they applied ML to the problem, you could see they got an instant win, which is just insane. And then, turn it off and it popped right back to normal. So they knew that ML was causing this. And if you're an average organization and you see this, you're like, oh my gosh, I need to use ML immediately. This is the greatest thing. Google's able to save hundreds of millions of dollars. Surely I can as well. Unfortunately, ML is quite hard. And the problem is that you generally see this. You have this magical AI goodness that's held out there for the universe, for the world. And on the left-hand side, you have most folks who are just using a Jupyter notebook, just using a downloaded model or a pre-built model with transfer learning and things like that. And it's very hard to bring it into production. And more often than not, what you see is something like this, where you have this big gap between, where the model is being developed and then ultimately rolling it out. And the problems basically come down to this. You have, on the left-hand side, you could either build your own platform for moving that from these downloaded models, which is great, but then you have to do it yourself. Or you can go off and build a proprietary solution, which sounds great, but then all of a sudden, you end up with the same problems you had in the first place. Now, we have heard this story before. We've heard this story many times in technology, but most recently, we heard it around things like containers and Kubernetes, where, for a long time, containers were very hard. You had to build your own orchestrator or use a proprietary one or something like that. But then Kubernetes came along and it kind of took over the world and everyone used it. And on top of that common platform, they were able to build cloud native apps. So it is my proposal that what we need to do is build cloud native ML that is highly performant, that is highly scalable, and can move in a lot of places and really bridge the gap between where things are developed and production. When I think about what the elements of what that would look like are, I think it breaks down to composable, portable, and scalable. I'll talk about those just very briefly. Around composability, you saw in many of the slides over the course of yesterday and today, folks are pretty aware that it's not just about building a model. It's about everything that folds into the overall system, where you have ingestion and validation and all of those various things, where a model is just a single component of it, and then finally rolling it out. And when I say composable, I mean a system that lets your engineers and data scientists pick and choose the things that they want. This is a public study that Microsoft put out around the number of unique tools inside Microsoft. And Microsoft has a fantastic platform for machine learning engineers, but they all want to use a tool that is meaningful to them for a particular step. And here in this case, one of the top ML organizations in the world, 159 different tools. So if you just give them a single platform and say, you got to use this, you're going to have a whole lot of unhappy people. Then we come to portability. And this goes back to the tweet. Once you get your entire stack built, which starts at the model or the pipeline or whatever it is, and goes all the way down to the hardware, detailing things like drivers and accelerators that you might choose, and every level in between, that pipeline is only a small subset of it. You might have a lot more to detail, which is a lot of work. And then you finally get it up and running. It finally is beginning to converge, and you're like, this is fantastic. Except then you have to reproduce it and create an entirely new stack for your large-scale training, and then a third stack when you end up rolling out to cloud. And oftentimes, if you're going to integrate lots of other environments as well, staging, test, so on and so forth, you might have more stacks to recreate again and again. And then finally, I like to talk about cloud native being scalable, right? When you hear scalability, you oftentimes say, I just want more infrastructure, accelerators, disk, networking, whatever. But that's not really the end of it, right? It goes beyond that. How do you scale to more programs? Here's a recent NeurIPS presentation about how many papers they are, going up exponentially year over year. Plus, internally, you're going to have many, many runs to compare, many experiments and so on, programs to compare against each other, particular models that you might want to test. And more skill sets where, you aren't just talking to the data scientists or the engineers, you're talking about SREs, you're talking about the engineers that are building an into your app. You're talking about compliance and legal and all these various things. All these are ways of increasing scale and things that you need to bring on to your overall platform. At the end of the day, you just want more programs faster, but there's a lot of elements to include there. So if we did our job right, we would build cloud native ML. Cloud native ML includes these three components. I like to say, what's really good at this is things like containers and Kubernetes, except, if you want to do that, a lot of times today, you have to learn a lot of stuff. And you're like, well, I'm going to just go use this hosted platform. I'm going to go use this proprietary stack, which is okay as well. It doesn't exclude you from having to learn all of these bits, which is super annoying and really not what a data scientist should be spending her time on. She should really be focusing on how to do, the best thing for my business. So I propose that we build something to give everyone cloud native ML, and that's what I call the SAME project, which stands for self-assembling machine learning environments. What that looks like is something like this, where you say, hey, you know what, I'm going to pick a backend. Maybe it'll be Kubernetes, maybe it'll be Azure Machine Learning's endpoint, maybe a SageMaker or Google Cloud or any kind of endpoint hosted in the cloud, and we're going to use that backend. And then I'm going to declare my system, my pipeline, on my local machine, and I'm going to be able to stamp that out into each of these places, and it will auto-configure itself based on whatever that backend I choose is. But as a data scientist, I know it ran locally, and because it ran locally, I know it can now run in the cloud. And we're going to make that commitment as part of our platform. Big companies solve this by building a large internal platform that often solves this for themselves. At Google, you have TensorFlow Extended. Facebook has FB Learner Flow. Uber has Michelangelo. At Microsoft, our platform is called Ether. These are hosted platforms with very rich developer environments, but they're very specific to those organizations. And oftentimes, even within an organization, it's hard to move from place to place. If you need to build your own platform or have your own deployment, it can be quite challenging to move an experiment that ran over there over to this other place, let alone if you want to do cross collaboration with academia, or offline work. So my proposal is to solve it for everyone, but I don't like doing things easy. Let's make it even harder, right? One of the things that I really want to take on is bringing it as far left as we possibly can, where we're not starting at just, hey, you have your model and it's already working. Let's get into the Jupyter Notebook. Jupyter Notebooks are the lingua franca of where this stuff happens. And anyone who says, oh, you know what, you can just do it in C or Python or whatever. Yeah, you can. And oftentimes you do it. But Jupyter Notebooks are great for a reason. They're great because they provide this wonderful local environment specific thing. You can do all the work that you need to. They're very, very far from production, but they're growing like mad. And more often than not, when you go out and you find an academic paper, or you find a best of breed model or something like that, it's going to be in a notebook. And so I want to meet developers and data scientists where they are. And I think that we need to start with Jupyter Notebooks, not just code. Now, to be clear, when I say Jupyter, I really mean the whole stack. It's a file format, it's an IDE, it's an execution kernel, and an ecosystem of associated tools. We're not going to change anything there. We're going to use the format and the system exactly as it is, but we're going to help bridge that gap and move it to production. So let me show you how this might look, right? Today, a model development process looks like this, where you have people starting over here. They're writing Jupyter Notebooks in one of these tools, Jupyter, the IDE, or PyCharm, or VS Code, or Eclipse, or whatever it might be. And it works. Then they take that, hand that to a developer who spends her time converting it into code that may or may not be an accurate representation. Then she'll take it and hand it to an SRE who builds it into deployment artifacts, puts it into a container or other deployment artifacts, including a runtime configuration. And only then does it get pushed to that hosting platform on the back end. And you have very, very many different hosting platforms here, as you can see. Ideally, we would change that. Our vision is to say, like, let's make it easy for those notebook developers to build that reliable application locally and then move it themselves into the production environment. Now, that doesn't mean necessarily deploy to production, but it does mean that the thing that they push into GitHub or into their Git and then convert, all that happens in an automated way through standard tooling, instead of this very manual process that goes back and forth. And by that, I mean, let's break it down into these various components. Let's make those notebooks portable. Let's capture the environment that you did, locally. No more, pip install random package. No more platform specific things that are undetected. Let's help move that to production with a reduction in boilerplate and helping those folks use better practices. And then finally, let's improve that pipeline execution. So as we make this conversion, it's not just throwing it all in a single container. Let's take advantage of things like parallelism, caching, and things like that these backends provide. And that's something I think we can do. So instead of this, you see this. A data scientist continues to work on her notebook. It works great. But when she's done, she says, okay, I'm going to push this off to that production platform. It auto converts it into deployment artifacts and then pushes it to the backend. And you can see some of the benefits there. Less inner loop, fewer boilerplate, you limit manual rewrites, and it takes advantage of all the wisdom that we have around software engineering, 12-factor app support, tool chains, and so on and so forth. All right, so with that, this is actually a live project right now. We do have real running code. I'm just going to show you a demo. We haven't open sourced everything yet. It will absolutely be open source. But let me show you what it looks like right now as we run it. Can you see this?
Yes, we can.
Okay. So what you see here, this is going to be a video because unfortunately it does take a little bit of time, but it's it's a recent video. This is recent code. To give you the layout, over here we have our standard notebook. No add-ons, nothing special, just Python 3. Up here we have VS Code where I'm going to write some text. And down here, we have a command line interface that we use to interact with the overall system. So as we go forward here.
So we're going to give you a quick.
Oh, sorry. You don't need to hear my voiceover. On the left-hand side, as I mentioned, that's a standard Jupyter notebook. It does all the things that you would do in your Jupyter notebook. It does printouts. It does logs. We define functions all over the place. We have images, all that various mess. And, it uses all the worst practices that data scientists have been doing today. I have used these many, many times. Printouts, logs, various things like that. We're not asking, as part of our project, these data scientists to change in any way. This will work perfectly fine for our purposes. Now, if I wanted to deploy this to something like Kubeflow or Azure Machine Learning or anything like that, today it would involve quite a bit of rewriting. So let's see if we can solve that. The first thing that we're going to do over here is we're going to write a very simple configuration file. Really, this is it. It's just about 11 lines of standard YAML. And in it, we decide to, define some of the important characteristics that you're going to need when you push this thing into your overall production system. This could be things like the name and version. This could be a pointer at that notebook that we mentioned earlier. It could also be things like the run and so on and so forth. So as you can see, it's pretty straightforward stuff, nothing terribly complicated. And that last line is really critical, where we're defining that parameter in code. Instead of doing it kind of like inline or as a command line interface, you now are able to check this in as your overall body and say, oh, this particular model that I built here, or this pipeline that I ran, it had these parameters associated. And you can log those to all the standard tools you normally do. We have MLflow support already. We want to add weights and biases and Kubeflow metrics as well. And we're obviously looking for whatever the community would like to direct us towards. But then finally we go to execute this on the command line here inside my thing. I've already installed the same binary, which is just a CLI called same. And I've already created a Kubeflow. I just used a very standard one, the default install of Kubeflow, nothing particularly complicated here. But after that, we're done. So here you can see I say same program run. It goes off, it pushes this notebook into that Kubernetes environment, into that Kubeflow environment, and executes it. And from there, you can see that I went forward and pushed it into Kubeflow. And you can see there, I took that single notebook, I injected a step before it that got me some run information. And then it actually went through and transformed the notebook into Python behind the scenes and put it into a single step. And it executed it now on Kubeflow. So that is with 0 changes from that notebook that ran locally. I'm now running this inside of a Kubeflow deployment, which it goes forward and executes. And you can see here, all those logs and printouts and things like that I was doing inside the notebook are in the logs. Now, we actually have more information than this. I just haven't supported it yet. We can print out images and things like that. The standard log visualization doesn't support that. But by default, this works, right? So let's go even further than that. How about we see about taking advantage of some of the things that Kubeflow provides? For example, one thing that you'll want to do with any pipeline system is support things like breaking these up into steps. So various things can be cached. You can run things with different base images. You can run things with different hardware providers. Well, what would that look like? In this case, what you do is you need to do you just add a metadata tag. This is in standard Jupyter. We haven't even added a plugin that says same step 1, execute this, and same step 2, execute here. And from that, what I've done is I've automatically added here information for same to go forward and execute multiple steps. Now, this definition says everything before step 1, we're going to call that step 1. Everything between step 1 and step 2, we're going to call that step 2. And everything after step 2, we're going to call that step 3. And you see here with 0 work, data scientists didn't have to know anything about the backend, didn't have to do anything. The system automatically now breaks it up into a 3-step deployment, each of which can be added and augmented in a way that is meaningful for that particular step. Now, we don't automatically infer what's necessary. Oh, this needs a GPU. That's still up to you. But without the data scientist having to think about anything, they can just simply say, hey, this step requires a GPU, and your team and the backend and whatever can figure out what to do from there. And this also gives you unprecedented levels of visibility. So, for example, here I built a very simple little example to show you how powerful this is. Here you can see I'm going to push this into a metadata backend. This is something we also support, where we detect what the context is as you pass from step to step through this. Again, the data scientist didn't have to do anything here. You just added that URL. And this is just a very trivial proof of concept example where I took that context in between each of those steps and pushed it in there. But you could wrap it with your own logging and whatever you might like. And you can see how this would work. You have same step 0, where all of those steps now are broken up. All of them are pushed to a back end. And I can debug, possibly even more richly than I can debug locally. Because here you can see in between each of those steps, I'm now able to trace individual variables and how they change from step to step. So between step 0, at step 0, before it started, B and A were undefined. Then in step 0, it became 15 and 10. Then in step 1, it entered at 15 and 10, and B converted to whatever 2500, 10, and 305, and so on. You get the idea. But at the end of the day, the idea is that this kind of automated breaking up, the data scientist didn't have to do anything here. It just automatically enriched the experience. And like I said, made it even easier to move to production. So that's the demo. Let's flip back. Can you see my slides?
Yeah, we can.
Okay, great. Like I said, demo summary. You saw me automatically grab all the packaging information. I did pip install throughout there. I did a bunch of imports. Super easy to forget it if you're like me, and 10 minutes later realize that you forgot to include in your requirements.txt. I do all that for you. Serialized it, captured environments, captured dependencies, and pushed it up. We also accelerated the path to production. So you had all your configuration in that single YAML file that auto created this backend and executed against it. It also you didn't have to do any complicated control flow like, oh, if in dev environment do this, if in production do this. All that's built in. And we have that CLI, which is extremely small and has almost no dependencies. So you can install that even in very locked down environments. It doesn't matter what version of Python or other you have installed, we'll take care of that for you. And then finally, improved pipeline execution. A data scientist, again, without any knowledge of parallel execution or DAGs or anything like that, just adds a few metadata tags, and they're able to get improved execution on the back end. A richer backend might look like this, where you talk about different environments, different mounts and things like that, data sets you might want to include, all those various things. And like I said, I think this last bit is one of the most important, where as you execute, you are able to capture the run or the experiment, and you push in not just the specifics of your run, but also the parameters and so on, all written down rather than being in code. We've talked to a lot of customers. We have a lot of interest in something like this, getting it to production and moving it out. But at the end of the day, our goal is to really have this be, the center of the Venn diagram. We want it to be open source governed. No single company should control this. No single company can control this, because if it only works with your particular backend, then that's a non-starter. It's got to be based on a universal platform. Things like YAML and Jupyter and so on and so forth that are already the way that people write these things. No new SDKs or other things like that have to be required. They can all be optional. And as you saw there in the notebook, we're going to offer some SDK and other plugins and things like that, but those are going to be totally optional. You can use just the vanilla one and it'll work. And then finally, it's got to be declarative, because you have to include all the things that are important, whether or not it's your requirements.txt, whether or not it's your environment file, whether, no matter what it is, that's what we need to base this on. Because if it's imperative, if it requires detecting what's on the back end, that's a likely going to be a blocker for moving it from place to place, because that means you're going to have to know, who's using what and at what time. So with that, I am out of time. I know I want to do this. I want to leave this up here. You're more than welcome to come join us. We are just getting started. The binary is out there. It is totally unsupported. You're welcome to mess around with it. The code is not out there yet, but the binary is, and the Slack is out there. If you're interested, come talk to me, and come join our repo, and email me if you'd like as well.